There. So we're going to jump into our last chapter of the semester, chapter 3 here. And it gets into a couple of different topics, but the first topic we're going to talk about is the idea of parabolas. And you guys have talked about parabolas before back in Algebra 1. You guys know what a parabola looks like. And we actually already talked a little bit about them when we talked about parent functions back in chapter 1, where you had to know what a quadratic graph looks like, cubic, absolute value, all those graphs we talked about when we talked about parent functions. Well, what today's lesson is essentially taking a quadratic equation from this form right here, which is what you guys are more familiar with, and putting it into what's called parabolic form, or standard form for a parabola. So parabolic form looks like this right here. So part of today's lesson is taking equations that look like y equals ax squared plus bx plus c, equations you're familiar with, and converting them to this form. And the question that comes up is, why are we going to convert from here to here? Well, I want to bring back an idea to you guys that we haven't talked about in quite some time. And you don't have to write this, I just want you guys to watch a little bit, okay? So we won't start writing on the notes yet, I just want you to watch. And I want you to remember the idea of shifting left and right and shifting up and down, and vertical stretching and vertical shrinking. How we can take a parent function, and if it's an inside change, we know we're shifting it left or right, and if it's an outside change, we're shifting it up and down. So it's a topic we've already talked about, but now we're going to tie these two things together. How we can take a parabola in parabolic form and have a very good idea about where it is in the coordinate plane and what it looks like. Meaning, if we have an equation in this form, we know a lot more about the parabola than if it's in this form here. So that's the general idea. We can sketch a better graph if we have it in this form. So to refresh your memories, the normal quadratic parent function is y equals x squared, and that's just your normal parabola with the vertex at the origin, okay, if you remember that. Then we talked about the idea of taking a quadratic or any parent function and shifting. And again, you don't need to write this, just want to refresh your memories. And so if we have an inside change, remember that this is going to shift your graph the opposite of this number horizontally this many units, which means this parabola would shift to the right 3 units and up 1 unit. It's the opposite of what you would think this would do and then whatever this would do. So we would take our parabola, and if we shift it right 3 up 1, that puts our new vertex right here at 3, 1. And then we can draw our normal looking parabola. So if we have it in this form, we know exactly where it's going to be. Whereas if we had it in the form we're familiar with, like this, we don't know exactly where it's going to be in the coordinate plane. So that's the gist, is from this form, we know where it's going to be and what it's going to look like. So for instance, this would shift our parabola to the left 2 and down 4. Left 2, down 4. So it puts our new vertex, left 2, down 4, right here. And then we just have our normal looking parabola. Now take a look on these two at how from parabolic form we know exactly what the vertex is going to be. So here the vertex is at 3, 1. We know that based on shifting. So think about how we can take our equation from parabolic form and figure out where the vertex is. Because that's the most important point of a parabola, is the vertex. So notice it's just the opposite of this number, comma, this number. So in this case, it's 3, 1. In the second case, this vertex is -2, -4. So again, the opposite of the number in the parentheses, comma, whatever the number is on the outside. If you throw a number out in front of the parentheses, remember what that does. That gets into your, is it going to be narrow? Is it going to be wide? Does it vertically stretch it? Does it shrink it? All these words that we've talked about. Well, first, let's shift our parabola, left 2, down 1. Left 2, down 1. And let's try to remember what this number does. Notice this is a 1/5 and this is a 5. Now, if it's a 5, or basically bigger than 1, that's going to make it really skinny. And the reason it does, because you're multiplying your values by 5, so it makes your y values that much bigger. So your y values get bigger quicker. But if you have an a value of 1/5, well, now you're not multiplying by as much, and so it makes it wider. So for this one, I know that it's going to be a vertex of -2, -1, and it's going to be a wide parabola. So we have a pretty good sketch, right? These are normal looking right here. This one's wider because that value is between -1 and 1 right here. This one, we know our vertex is going to be at positive 4, negative 1, because it would shift to the right 4, down 1. And since that's a 5, it's bigger than 1, that means we're going to have a pretty skinny looking parabola right here. Makes it really narrow when that number is big. The last thing that happens is if that a value, that number in front of the parentheses, is negative. And if it's negative, remember what that does, that makes your parabola be upside down, like an N shape. So we're still going to have the same shifting. Our vertex will be at negative 1, positive 4. We know it's going to be an upside down parabola because this is negative. And we know it's going to be skinnier because this number is less than 1. So it's going to, or I should say less than negative 1, I'm sorry. Anytime your a value is above 1 or less than negative 1, it's going to be skinny. If it's between negative 1 and 1, like a fraction or a decimal, it'll be wider. So it's going to be skinny and upside down. So that's the gist, just showing you guys how if we have equations in this form, we can draw a really good sketch of our parabola. Okay? So let's jump back to the notes and talk about how we adjust to get it into that form. Well, look at the equation first of all, just some variables to talk about. Notice you go from an A, B, C, and now we're shifting over to this form here, where A here and A here are actually the exact same A values. And you'll see why based on how we accomplish our task. But here we have x minus h and plus k. And notice that h comma k is the vertex. It says minus h here, yet positive h is the vertex. That sign changes because you would be shifting to the right h units, positive h units, and up k units. So it's always the opposite of the number in the parentheses, the vertex, comma, the number on the outside. All right, so let's look at the directions. For the following, find the vertex, axis of symmetry, is it opening up or down, is it wide or narrow, find the x-intercepts, otherwise known as the zeros, and graph. So we have a lot to do in each problem. There's a lot. But before we do any of this, let's put this equation into parabolic form. All right, and it is a procedure, and here's how this procedure works. I got some steps to do. So step 1, we're going to move the constant to the other side. So we're going to subtract 11. So y minus 11 equals 3x squared minus 12x. Step 1, move the constant over. Step 2, factor out the a value from the remaining terms. Now that doesn't mean we're going to take the GCF of the right side. We're only going to factor out the number because in parabolic form, we have this a out in front that's factored out, and that's what we're going to do right now. We're going to factor a 3 out of the right side. So y minus 11 equals 3, and then x squared minus 4x. And I'm going to leave a little space behind the 4x. And here's why. Think back to this chapter we just did on quadratics when we did completing the square. Remember what completing the square did? It gets you this quantity squared. The whole point of completing the square is to get to a quantity squared. And I said at the time in quadratics, it's not a method I would ever choose to voluntarily use to solve quadratics, but it's a process that you have to know how to do for future problems. And that's right now. We have to know how to do this process to convert from one form of an equation to another. And it'll show up again second semester. So it is a process we have to know, even though it's not the best for solving quadratics. So at this time, we're going to complete the square inside the parentheses. Remember what completing the square means. We want to create our own c value right here. All right, we want to create a c value right here. So we take half of b and square it. We take half of 4 and square it. And we get a positive 4 plus 4. Now this step 4 is kind of wrong. It says add this number to both sides. That's kind of false. I regret putting that step in there. We do have to add something to the left side, but it's not 4. Think about what we actually added to the right side of this equation. Just think about it. What did we actually add? And we did not add 4. We added 4 3 times. Like if I would distribute this 3, we actually added 12 over on the right side. So to figure out what you need to add to the left side, multiply your new c value and your a value together. So we actually added 12 here. So we have to add 12 to the left side to keep the equation balanced. So it really shouldn't say add this number to both sides. Well, again, think about completing the square. When you create that c value, Now you can factor the parentheses and get that lovely quantity squared. So let's combine these constants over here. Y plus 1 equals 3, and then let's factor. And this is going to become x minus 2 squared. And we're almost there. Last step, solve for y. So subtract the 1 over to the other side. So y equals 3, x minus 2 squared minus 1. So it is a process that you look at it and it's like, man, that's a lot. And it is. But, after you do, 3 or 4 of these, it is a procedure that you just tend to remember. Kind of like the quadratic formula. When you see it right at the beginning, it looks messy and scary, but after you do it several times, you're just plugging numbers in and using your calculator. Same idea here. After you do this a few times, it just becomes kind of second nature. So now from this, we can identify all the information we need up here. It says find the vertex. Well, the vertex is the opposite of the number in the parentheses, so 2, and then -1. So we can plot our vertex at 2, -1 on the coordinate plane. Let's see what else it asks us to find. The axis of symmetry. We haven't really talked about that yet. Hopefully in Algebra 1 maybe you did a little bit, but remember every parabola is symmetrical, which means if you have a parabola, there's some line that cuts your parabola in half. And if you have a parabola that opens up or down, it's a vertical line. So when it says what's the axis of symmetry, it's asking for the equation of the line that cuts your parabola in half, this vertical line. And so it's going to be, well, think about vertical lines are always x equals, and it's going through the x coordinate of the vertex. So for this one, our axis of symmetry is x equals 2. Don't just say 2, but name the line as x equals 2. That's going to be the vertical line that cuts our parabola in half. Now it says the direction. Does it open up or down? Well, the a value determines that. Since a is positive, our parabola is going to open up. Then it says the shape. Is it going to be wide or narrow based on the parent function? Well, anytime this a value is above 1 or less than -1, it's going to be more narrow. The y values are going to get bigger. It gets stretched out. So narrow. So we already have a really good idea that our parabola is going to look like this, but we can go one step farther and find where it's going to cross the x-axis. That would give us a couple additional points to plot here. Notice it says find x-intercepts. Well, this goes back to last chapter. Anytime you want to find x-intercepts, you put 0 in for y and then solve the equation. So I'm going to plug 0 in for y right here. Or you can actually plug it into the original equation either way. That's completely up to you. If you plug it into the original right here, you'd probably just use quadratic formula right off the bat. If you plug 0 in for y here, we can solve. And so that's completely up to you. But plug 0 in for y. I'm just going to use this one. And now I want to solve this. So I'm going to add 1 and divide by 3. So 1/3 equals x minus 2 squared. Added 1 divided by 3. Now you can square root both sides. So x minus 2 equals plus or minus square root of 1/3. And then add 2. Those are the exact x-intercepts. Basically, that means those are the numbers where it's going to cross the x-axis. However, I don't know where 2 plus the square root of 1/3 exactly is on the x-axis. So while I would state these are the x-intercepts, I want those to be exact, I would probably take my calculator and figure out what those decimals are. So 2 plus square root of 1/3 is about 2.58. So right here. And then 2 minus square root of 1/3 is about 1.42. And you can see how skinny that parabola is right here. So from parabolic form, we can get a whole lot more information than we can just from the regular equation. All right, let's practice. We'll skip example 2 there, just because of time. Example 3, let's put this into parabolic form. Okay, so remembering our steps here, I'm going to move the constant over. I'm going to treat this like it's a y instead of writing f of x. So I'm going to have y plus 9 equals negative 2x squared plus 12x. So move the constant over. Step 2, we want to factor the a value out of the right side. So y plus 9 equals negative 2. Now be careful when you factor out a negative. It's going to flip that second sign, so minus 6x, and leave some space to complete the square. So move c over, factor the a out. Now complete the square. Find this number we need to add here to make this a perfect square. So half of 6 is 3. 3 squared is 9. So I'm going to add 9 here, which means we have to do something to the other side. We don't add 9. Think about what we actually did. We actually subtracted 18 from the right side, because if you would multiply this negative 2 and this 9 together, you get negative 18, which means we have to subtract 18 from the left. So now we have y minus 9, when you combine those numbers, equals negative 2. And now we could factor this. The whole point of creating that c value is to factor this perfectly. X minus 3 squared. And then add the 9 over. So we get y equals negative 2, x minus 3 squared plus 9. So there's our parabolic form. And now we can answer all those questions. So we know our vertex is going to be positive 3, positive 9. The axis of symmetry, it's going to be that vertical line that cuts it in half, going through that x coordinate of the vertex, so x equals 3. It said, does it open up or down? Well, since a is negative now, you have a negative a, so it opens down. It's going to be narrow because this number is less than negative 1. So anytime it's between negative 1 and 1, it'll be wide. Anytime it's above 1 or less than negative 1, it'll be narrow, skinnier. And then we can find x-intercept. So I'm going to plot what we know so far. We know the vertex at 3, 9. And we know it's going to be skinny and do something like this, but we get a really good depiction if we could figure out the x-intercepts. So last time I set the parabolic form, the y equal to 0. Well, this time I'm just going to set the original equal to 0 just to show you that you do it either way, and I don't care how you do it. So I'm going to use the original equation on this time. It does not matter. But if I do this, then for me, I'm going to use the quadratic formula. If I would have plugged into this one, then I would have subtracted 9, divided by negative 2, square rooted, did all that I did on the last problem. Here I'm going to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac. All over 2a. Left you in suspense. Alright, so we have x equals negative 12 plus or minus, let's see here, take out my handy dandy notebook. Minus 4 times 2 times 9. It's 72. Square root of 72. I could simplify the square root of 72. 36 goes into that. So this would be negative 12 plus or minus 6 radical 2 over negative 4. And to fully simplify, you could divide all of these integers right here by 2. So negative 6 plus or minus 3 square root of 2 over negative 2. So these are the exact x-intercepts. All right. So if the question asks for that, I want the exact x-intercepts. However, if you're going to plot these on the x-axis, you need to know where these are. So enter them in your calculator. You don't need to show it, but I'm going to do negative 6 plus 3 radical 2 divided by negative 2, and I get about 0.88. And then do negative 6 minus 3 radical 2 divided by negative 2, and I get about 5.12. Feel like I did something wrong, because it should be symmetrical, right? So over, oh no, that's right. Because anytime you graph, I was just kind of off to the side here, but if I look at it straight on, notice that it is symmetrical. If you find one x-intercept to be here, and the other one to be way off over here, you know you did something wrong, which is what I thought would happen, but no, that's good. Here we go. Here we go. For you Mario Kart lovers. There you go. So from that parabolic form, we can get a whole lot more information. What I would encourage you to do is to, and I won't know if you do this or not, but I'd encourage you to pause this video and try this one and just put it in parabolic form. We won't go through all of the analyzation, but I know that the bigger part of this lesson, the harder part, if you will, is converting this to parabolic form. So why don't you pause the video, put it in parabolic form, and then push play again and see if you did it right. Okay, so let's see. We should have had subtracted 5. Factor out the 1/2. Now here's where you need to be very careful. If you factor out the 1/2, the most common wrong thing students do is right here they put minus 2x. But when you factor out a 1/2, you're not taking half of 4. Think about what you're doing when you take out a GCF. Like when I took out this 2 right here, now I know if it was a negative 2. When I take out this negative 2, to figure out what's left, I do 12 divided by negative 2. Well, if I do negative 4 divided by 1/2, that's the same as multiplying by 2. So be careful here. So what's left here would be minus 8x. And understand why. If I would distribute this 1/2 back inside, I should get back to where I started. And if you put a 2 here, you wouldn't get back to the 4x. So I would erase that if you did that part wrong. Now take half of 8 and square it. So add 16. But you're not going to add 16 to the left. You're going to multiply 1/2 and 16 together, get 8, and that's what you add to the left. So you should have y plus 3 equals 1/2, and then factor x minus 4 squared, and then subtract the 3. So y equals 1/2 x minus 4 squared minus 3. And from here, you could go through all your analyzation and whatnot, but I'll save you the time. But you know that it's going to open up. You know the vertex is at 4, negative 3. You know it's going to be wide because that's less than 1. And then you can use quadratic formula and find your x-intercepts. So just doing all the same thing we did over in the other problem. But remember, just knowing how to get it into that parabolic form. All right, a couple different questions. A couple different ones. So we're done graphing on this note outline. So example 5 says, find the parabolic form. Find the equation of the parabola that has a vertex at 1, negative 2 and passes through the point 3, 6. We did problems like this when we did circles. I don't know if you guys remember that, but they gave you a whole bunch of information. You know, maybe they gave you the endpoints of the diameter, or they gave you the center point and a point on the circle. They gave you various information, and you had to write the equation of the circle. It's the same principle. We want to first, I would write out the parabola equation, the parabolic form. It's y equals a times quantity x minus h squared plus k. And think about what they're giving us. If we're going to write the equation, we need to know two things. We have to know the vertex, we need to know h and k, and we have to know this a value. Well, they already tell you h and k. They already tell you the vertex. So they give you half the problem already. Here's h, here's k. Your vertex always hk. So plug those in for h and k. So here's what we know so far. We have y equals a, and then x minus 1 squared. Notice if the x-coordinate is positive 1, it becomes minus 1 in the parentheses. And then minus 2. K is exactly what the value is. So now we need this a value. Well, they gave us this information over here for a reason. Think about any graph in the world, any equation of any graph in the world. X and y stand for points on that graph. And so if it's passing through the point 3, 6, they're giving you x and y. That's why they're giving you that. So plug those in for x and y, and then you can find the a value. So 6 equals, we don't know a, x is 3. Now we can solve this. So we have 6 equals a, 2 squared is 4, minus 2. The most wrong thing I find students do in these problems is they will subtract this 4 and 2 right here. They'll say, oh, this is 2a on this side. Well, no. A better way of writing this to avoid that issue, put that 4 in front of the a, because that's technically where it should be anyway. So it would be 6 equals 4a minus 2. And that's just going to avoid the issue of accidentally subtracting those. So add 2 and you get 8. 8 divided by 4 is 2. So a is 2. So to write the final answer, just pop that 2 right where that a value is right here. When you write the equation of something, y and x are always going to be in your equation. There it is. So take what you know and use it to find your equation. All right, last one. The daily cost of manufacturing a particular product is given by this cost function right here, where x is the number of units produced each day. So basically you're making something, and this equation is going to tell you how much it's going to cost you to make that many things. All right, let's say you're making hats. All right, you're making hats. And if you make, 10 hats, it's going to cost you a certain amount. If you make 30 hats, it's going to cost you a different amount. How many units should be produced to minimize cost? What is the minimal cost? So how many units should be produced to minimize cost? What is the minimal cost? So think about what this question is asking. I want you to think about this graph. You don't need to graph it, but I want you to think about this graph. It's going to be a parabola because it's x squared, and it's going to open upward. And this graph's going to do something like this. All right? And we're looking for this point right here. Think about what answers the question. How many units should be produced to minimize cost? Essentially, this question is saying, what's the x value of the vertex? Anytime you're doing quadratic application problems, you need to think about what is the question really asking you to find. How many units should be produced to minimize cost? So it's saying, what's the x value of the vertex? And then it says, what is the minimal cost? Well, that's the y value of the vertex. So really, this question is saying, find the vertex of this equation. Now, there's two ways to go about it. Okay, there's two ways. You can do what we did on the previous problems and put it into parabolic form and then just identify the vertex. All right, that's option one. Option two, you may have learned this back in Algebra 1. So option one, write this out. Option one, put in parabolic form. And then identify the vertex. And then just know which, the x value is the first part of the question, the y value is the second part of the question. Option two is this. There's a formula that hopefully you learned in Algebra 1 that finds the vertex for you, because you graphed parabolas in Algebra 1 without ever talking about parabolic form. You graphed these. You found the vertex some way. And here was probably the way that you did. There's a little formula. X equals negative b over 2a. That was option 1. Here's option 2. And I don't care how you do it. This little formula right here, it's basically the quadratic formula without the radical part. This finds you the x-coordinate of the vertex. This finds x-coordinate of the vertex, which is what we're after. That's what answers the question. We're not graphing anything, so you don't need to put it in parabolic form. Just find the x-coordinate of the vertex to answer the first question. So do this. So in this problem, x equals negative b, so positive 7, over 2a. Well, a is not 1200. A is the number in front of x squared. So over 2 times 0.1. This is just another way to find the vertex. So 7 divided by 2 times 0.1 is 35. What that means is 35 units should be produced to minimize cost. So 35 units. And then it says, what is the minimal cost? Well, think about how you use functions in general. Functions are used if you know an input, plug it into the function, and you get the output. And that's what we're looking for here. If 35 units are produced, plug 35 into your equation and figure out what the cost would be. So take out your calculator and put 35 where these x's are. So basically we're looking for the cost of 35 units. So we'd have 1200 minus 7 times 35 plus 0.1 times 35 squared. And I'm just going to plug that all into my calculator. 1200 minus 7 times 35 plus 0.1 parentheses 35 squared. And I got $1,077.50. So if you make anything more than 35, it's going to cost more than this. If you make anything less than 35, it's going to cost more than this as well. There you go. So just a couple things to remember from this lesson. The whole idea, we're converting to parabolic form or standard form for a parabola. That helps identify the vertex really quickly. The direction it's going to open, the shape of it, all that jazz. There you go. Good luck.